Hi, hello everyone. My name is Elydio Soares. I'm a graduate student at the Federal University of Minas Gerais. I'm doing my master's degree in nuclear science and technique on the nuclear engineer department. The supervisor of my research is Professor Thelma Fonseca. As part of my research, I'm going to talk about the evaluation of the exposure dose indoor by inhalation due to exhalation of radon gas by tailing from niobium exploration in Araxá City, state of Minas Gerais, Brazil. On this presentation, I'm going to talk about the radon health risk, the objective and material, the equipment methods, the resultant discussion and conclusion. The radon health risk. The exposure to natural radiation. So we are constantly exposed to ionizing radiation that occurs in Earth crust and the atmosphere. Natural radiation is responsible for annual dose of 2 millisieverts a year. To understand the importance of the radon, 1.3 millisieverts of the total of this dose that we receive naturally comes from the radon. According to the United Nations Scientific Committee, the radon is the second cause of lung cancer. What happens is that the radon is alpha decay particle and also decaying polonium-214 and polonium-218. In both it's alpha decay particle also. Once the radon is inside the lung, it starts to disintegrate. The alpha particle can travel too far, but it can deliver a lot of energy to the closed cells. Because of that, the radon and its progeny is very harmful for the cells. Once the radon is inside the lung, the damage occurs for decades. As you can see here, the lead 210 takes 22 years to decay and keep going, and then it can keep going alpha decay particles inside the lung. The objective and material of this research. Before I talk about the objective and material, let's talk about the sustainability, because this is the reason that I use that material. In terms of sustainability, the reuse of discard materials or the use of waste generated due to the extraction of different ores is considered a possible solution in discovery of new materials research. The idea is to use the waste from niobium exploration mine as a raw material for mortar production at the construction industry. The alternative leads to cost reduction and provides an environmentally sustainable solution. The reduced exploration of natural resource and reduce of the waste of the production. That's the idea to use that material as a sample for this research. So the objective of this research is measuring the radon exhalation rate from the niobium mine waste. The samples were provided by the niobium exploration industry located in Araxá City. It's in southeast of Brazil, and it's over the exploration. It's from a geological formation called pyrochlorine. Detailed analysis on this research came from the process that they use inside the industry to separate the niobium from the waste. Inside the whole process, there is two parts of this process. That one called flotation process for the separation, and another one called the magnetic separation. So I get one sample from the flotation separation and another sample from the magnetic separation. The equipment and the method. The experimental method is the closed chamber. It's a measuring random radon concentration as a function of the surface area of the sample and the volume of the chamber. The waste sample were placed in the chamber and it was connected to the alpha guard detector. The detectors operate as a post-counting ionization chamber. The detector was set to operate in the flow mode with 10 minutes of display. The detector and the chamber with the samples were connected by tube to the flow pump that operates in 1 liter a minute. So that system operates in constant flow. So the pump blows the air through the chamber and goes to the filter, go back to the detector and out again and goes to the pump, and then this is keep going for 48 hours. After the measurement, the average concentration is determined and the exhalation rate can be calculated as a function of the volume of the chamber, the decay coefficient of the radon, the surface area of the samples. So that's where we can get the average concentration from the detector, and then we can calculate the exhalation rate of the sample. So to estimate the dose related to the radon gas inhalation as a function of the radon exhalation rate from the material that we just found out in the laboratory, we have to extrapolate these results to the room size in the ambient condition. So to do that, we use that formula that's related to the active concentration of the radon as a becquerel for cubic meters, with the exhalation rate we just found out as becquerel square meter per hour, in the surface area of the walls in a supposed room, in the volume of the room, and the coefficient of the exchanger air inside the room. Once we have the concentration of activity of radon inside the room, we can use that on that formula and to estimate that what's going to be the exposure dose for someone that lives on that room for a year. That's the way we found out our results. The results that we found on our experiment, it's shown here. So we have the average concentration of the radon from the exhalation rate on the dark sample is 2.056. In the light sample, from the exhalation rate, we have the concentration of 1.97. Using that formula that we talked before, we found out the condition on the real room will be 10.37 of concentration activity radon for light samples. If we have all the walls covered with that tailing. If you have the walls covered with the dark samples tailing, we will have the 11.43 exhalation rate. It means becquerel for square meter per hour, the rate. That's going to make a concentration of activity of radon inside the room, 41 for light samples and 45 for dark sample. Using that formula, this is going to provide for estimation dose of exposure were 0.74 millisievert a year for light sample and 0.81 millisievert a year for dark sample. Remind that this is it's a extrapolation of the laboratory results if we have the walls covered with detailing. With the results, I compared the results with another studies from different countries. So for the exhalation rates from another building materials that they studied in Ecuador, they found out exhalation rate is minimum on brick 0.05 and maximum in granite 7.83. In Libya, they studied the ceramic and they found the minimum exhalation rate at 0.07. In granite also is the highest one, 1.72. A study in Nigeria, they found out a minimum in gypsum, 1.63, and also a maximum in granite, 5.32. Sorry. The tailing from Araxá has a higher exhalation rate than many other materials used in these other countries. So to compare also the exposure of the dose, I use another study, and that this in Brazil. They study the exposure dose in many dwellings locations from different cities in different states. So the minimum dose was found in the Niterói city on the Rio de Janeiro state, 0.3 millisieverts a year. The maximum dose was found in Araxá city, the same city that has provided the samples that are using this research, was 16.7 millisievert a year. But regarding the risk of the radiation dose to the radon gas inhalation due to the concentration of radon activity, the standard reports for exposure to environment radon, they have limits, and it's different from country to countries. For example, in Brazil and so other countries, the concentration maximum has to cannot exceed 300 becquerel per cubic meters, and the dose levels to consider a free radiation environment cannot exceed 1 millisievert a year. So using that numbers, we can see that the light sample, even concentration 42, it's less than 300. And the dark sample 45 also is less than 300. And for those exposure dose, both samples, they have an exposure dose less than 1 millisievert a year. To conclude this work, we consider only the indoor radon concentration limit recommended by the standards. The study results found in the tailing are below the levels that represent a healthy risk in terms of dose exposure from radon gas inhalation. The idea of using tailing from niobium mine is a raw material for production of mortar by the construction industry, a sustainable form of production, will result in a final product that has a different random exhalation rate that was found on these tailings. In order to know the exhalation rate of mortar product from tailing, new tests must be conducted. The values determined in this study only accounts for radiation due to alpha particle emission from radon. For a complete radiometric analysis of the sample, further tests must be performed to collect the gamma and beta radiation data. I would like to acknowledge the institution and foundation that financially support this research, also the laboratories and institutes that help us with the experiments. Thank you. I would like to thank you for having me here and listening to this presentation. Thank you.